And these algorithms and the formulations are applicable to both TOARP and COP. We showed applications to coverage of linear infrastructure, such as road network, and for environment monitoring. So let's look at the dirty laundry. We performed empirical evaluation of the greedy algorithm, but we do not have any theoretical guarantee. We can find better methods to represent the information for environment monitoring by developing new methods for modeling of rewards and weight functions. Future work includes cleaning up the dirty laundry by developing approximation algorithm, and developing new methods to formulate reward and weights, particularly for environment monitoring. We also are interested in looking at higher order correlations, because right now we just considered quadratic correlations. And also we are interested in online version of the problem. Thank you.
Thank you. Are you good? Do you want to clip it on, or you want to hold it?
Good. Yeah, that's all.
Our next speaker is Xiaoming Jing. He's going to talk about He's going to talk about glide generalizable quadrupedal locomotion in diverse environments with a centroidal model. Go ahead and take it away.
Okay, so hi everyone. So today I will present our paper, and this work is a collaboration between all these wonderful institutions. Okay, so before I go into the details, let me first give you an overview of reinforcement learning for locomotion control. So in reinforcement learning, we try to learn a policy pi. And in this case, we usually parameterize them by a neural network. And the input to a policy is the state of the robot that we want to control. And the output of the policy is the action that the robot will take to interact with the environment. And the goal, in addition, the robot will also provide a reward to the policy as feedback. And the goal of reinforcement learning is to maximize the sum of rewards over some time horizon. So there are several challenges of applying reinforcement learning to real robots. So first of all, as our robot gets more complex, so we have a lot of degree of freedom on the robot. So we need to collect a lot of samples in order to get enough data to train the policy. So it's only feasible to collect those data in simulation. Otherwise, you can easily break your robot. This leads to the second challenge, the sim-to-real challenge. So all simulations are wrong. And mostly when you collect data in simulation, the policy usually doesn't just directly work on the real robots. So people spend a lot of time to tune their simulation model so that it's more accurate. And even that is not enough, and you need to do some randomization in simulation so that your policy is robust to this sim-to-real gap. And finally, we have the challenge of reward design. We need to tune our reward really carefully in order to get the behavior that we want on the real robot. So a lot of the existing work out there is what I will call full model reinforcement learning, in which case they will build a very detailed full order model of your robot in simulation, and then they will do Monte Carlo rollout in this simulation to collect data to train the policy. And if you are not careful with your reward design, you can get some really funny behavior on your robot. So here, the reward is just to check a desired velocity for the robot. And actually, this policy achieves perfect reward in terms of checking the desired velocity, but clearly, nobody will want to put that motion on a robot. And the solution seems to be reward engineering. So if you look at papers that actually come up with a system that can generate policies that work on a real robot, and you look at their papers, usually they dedicate a whole page of their paper just to describe the reward function. And even if you tune your reward function carefully and you generate a capable policy, because you build a very detailed model of your robot. So this policy will only work on this particular robot. And if you make small modification to your robot, in this example, we invert the knee of the hind leg of the robot, and the policy wouldn't work, and you need to train everything from scratch again. But wait a minute, model-based community tells us that a capable model is all you need. You don't need a full order model to come up with a capable policy. So why don't we just use that to train our use reinforcement learning on this model to train our policy? And so first, let me define the centroidal model that we use. So in the centroidal model, the robot is abstracted as a single rigid body model. So with 4 massless legs attached. So first we made the following assumption. The context sequence is pre-specified. So we know the robot is either doing trotting, pacing, or walking gait. And this allows, so this means that at each moment in time, we know exactly which set of legs is in stance phase and which set of legs is in swing phase. This allows us to divide the controller into 2 controllers, the stance foot controller and the swing foot controller. So for the stance foot controller, the input to the policy will be the state of the rigid body. And the output of the policy is the desired acceleration of the rigid body, meaning the linear acceleration and the angular acceleration of the rigid body. And because the system is under-actuated, we cannot just generate any desired acceleration we want. This will go into a QP solver that generate a set of ground reaction forces for the stance foot so that it can generate a acceleration that's as close to the desired acceleration as possible. For the swing foot control, the input to the swing foot controller is also the state of the rigid body. This will go into a foot placement strategy. In this case, we are just using a simple Rebel heuristic, and the output is a desired position of the swing foot. Now, with this centroidal model well-defined, we can now do Monte Carlo rollout using this model. And the advantage of using this centroidal model instead of a full order model is that it's faster to simulate and easily parallelized so that we can collect data real fast. And also, we only need to regularize the behavior of a single rigid body instead of worrying all the degree of freedom that you need to worry about on the full order model. But it also comes with disadvantage. For example, it doesn't know the notion of drawing or torque limits. So if your task requires the robot to operate on those limits, then it probably will fail. And then we also can assume a fixed gait timing. So it's always doing this trotting gait or pacing gait, and depends on your task, it might not be optimal. But in our scenario, we find this advantage is not a problem. And eventually, we want the policy that work on this simplified model to transfer to the full order model. But that's pretty simple. We can just do Jacobian transpose for the stance legs to transform ground reaction forces to joint torques. And then we do position control for the swing legs. One good thing about this centroidal model is that once we train this centroidal model on a simplified policy on this centroidal model, it can generalize to different configuration of the robot legs. And we can also efficiently train policies to try to tackle this challenging stepping stone terrain. So the policy is trained on the centroidal model and can directly deploy on the full order model in simulation. And we also have this example of asking the policy to cross this balance beam. And finally, we also have an example of a two-legged balancing problem, which you can consider that as a more complicated acrobat. And of course, we want the policy to also work on the real robot, but that's pretty straightforward. The centroidal model doesn't care whether your full order model is in simulation or a real robot. In this case, the same policy can work on simulation and, sorry. and directly deploy on the real robot. And it's pretty robust to unknown terrain. So we just put some obstacles on the floor and the policy can handle it pretty well, even though it's trained on a very abstract centroidal model. We don't have a perception system required to do a full stepping stone test on real robot, but we come up with this proxy test. So it's just asking the robot to cross this gap. So let me also briefly give you an overview of what we are working on now. So you remember the limitation of this model is that it assumes context sequence is pre-specified, and we also have this foot placement strategy that needs to be tuned. So maybe if we can also learn the context sequence, so like a policy to decide whether one foot should be in swing phase or stance phase, and also use a policy to decide where we should put our foot, we can get better policy. So here is a table of comparison. So in the first column is a heuristic where everything is not learned, including the body acceleration, which is tuned with a PD controller to track a desired velocity. And it works pretty well on continuous terrain, as been shown by many work in model-based control literature. No matter how hard we try to tune the controller, we find that it is hard to make it cross this challenging stepping stone scenario. But with our glide framework, so we have a policy to learn the desired acceleration, then we can generate a very stable walk across this stepping stone terrain. However, because the context sequence is pre-specified, so it's always doing this trotting behavior, no matter what command velocity we use. So for example, when we command the velocity to be 0, we want the robot to be standing still in order to be optimal in terms of energy efficiency. So we have another policy that also learn the context sequence. So a policy decide whether a foot should be in stance phase and in swing phase. And now, and now we get a behavior where when the command velocity is 0, it will do the standing gait. And when we ask it to walk forward, then it will directly use the trotting gait automatically. We also train a policy to cross this long gap terrain where you can see it could be pretty challenging to use a trotting gait to tackle this terrain, but our policy learns some sort of galloping gait, I think, to cross the terrain. And as we replace more components with learning-based components, it gets better and better. And we are still in the progress of replacing the foot placement strategy with a learn components. And hopefully after that, we can get the best performance. So to summarize, we find that reduced order model can be effective for reinforcement learning, and integrate model-based controller can simplify design process. So now go to the dirty laundry part. So the question now I ask myself is, do we really need to use this simplified model? So why do I ask myself that? So first of all, the robots are getting better. Even bad motions can work on the hardware. So if you look at some of the recent work that use reinforcement learning to train policies for quadrupedal robot, their motion is really, really bad. But it works on the hardware because our robot is just getting better. So maybe it doesn't matter whether we have good motion quality or bad motion. And if you remember in our pipeline, we have a Qt solver that makes the whole process kind of slow compared to just using a full order model and then just do joint torque control. So the benefit of using a simplified model become less obvious. And finally, simulations of full auto model are just getting faster and faster.